Welcome to Maths with EJD. In this video, I'll be talking about generating functions in algorithm analysis. Okay, so that's an application of generating functions that is really very important. Okay, so let's go for it. First of all, let's see an overview of what this is about. In algorithm analysis, generating functions are helpful tools for solving recurrence relations, which are commonly found when analyzing runtime of recursive algorithms. By converting recurrences into generating functions, we can find closed form, we can find closed form solutions and gain insights into the algorithm's runtime behavior. Okay, so let's look at some key concepts associated with this. So a generating function for a sequence f of n is a formal power series defined as g of x equals summation from n equals 0 to infinity of f of n x raised to power n. So it's still more like the classic definition we've always had. Then generating functions allow us to manipulate the sequence algebraically. And extract useful properties such as the asymptotic growth of the sequence. Like we saw yesterday, right? I mean, in the previous video, not necessarily yesterday. In the previous video, we looked at inversion for how we can use inversion, right, for solving complex problems. And we saw how the coefficient of a particular um, generating function was increasing. That's something like the asymptotic growth or something also. Okay, so let's talk about now Fibonacci, Fibo, Fibonacci sequence and runtime analysis. Trying to squeeze that in there. All right, so I mean, I think that works. Okay, so the Fibonacci sequence, I mean, this has come up a lot since we've been talking about generating functions. The Fibonacci sequence follows the recurrence f of n, which is equal to f of n minus 1 plus f of n minus 2 with f of 0. Of course, these are the starting values. F of 0 equals 0 and f of 1 equals 1. So we will use generating functions to solve this recurrence. So this is a recurrence equation right here. So we use generating functions to solve this recurrence and determine the asymptotic growth of the sequence. Okay, so the generating function of the Fibonacci sequence is g of x equals summation from n equals 0 to infinity of f of n x raised to power n. So we can write the Fibonacci recurrence relation as f of n equals f of n minus 1 plus f of n minus 2. Now this leads to the generating function so it leads to the generating function g of x minus f of 0 minus f of 1x. Trying to think about this. Yeah, minus f of 1x. Now, and because so f of n itself now corresponds with this particular value, and that is equal to, now for this one, that is f of n minus 1, so that results to x g of x. Then this other one goes to be x squared g of x. Okay, so, and we already know f of 0 and f of 1. We know f of 0 is 0 from the very definition. F of 0 is 0, f of 0 is 0, and f of 1 is 1. So this is 0, and this is 1. So if that is the situation, then we know that, okay, let's just remind ourselves, since f of 0 is equal to 0, and f of 1 is equal to 1, we get, we now get g of x equals, I mean, g of x minus 0 minus 1 times x. Let's just put that minus 1 times x equals xg of x plus x squared g of x. So that means that we have g of x minus xg of x minus x squared g of x equals x on the other side, or we can still tidy that up. So the missing link will be that this is g of x minus x equals x g of x plus x squared g of x. So we now transfer all these ones to the other side, and then we transfer x to the right hand side. So this goes to the right hand side, and then we have this next one now. So g of x is common here, so we have g of x. I guess I want to color code right here. Right. So now I have g of x into 1 minus x squared equals x. So the g of x now, so g of x now is equal to x all over 1 minus x squared. So this is a very important solution for the generating function. Okay. Okay. We still have a long way to go. Now that we have now that we are talking about runtime. Now that we have the generating function, we can analyze the growth of the Fibonacci sequence. The closed form expression of the generating function shows that the Fibonacci numbers grow asymptotically like like big O of phi n, and that's when we talk about runtime in computing. So big O of phi n, where phi is the golden ratio. Phi is the golden ratio. So that phi is actually 1 plus root 5 divided by 2, which is approximately 1.618. Of course, this is obtained from this particular expression. This is obtained from when you set that 1 minus x squared, 1 minus x squared, if you set it to 0 and solve. So you have 1 minus phi squared equals 0. If you solve this, you get that phi, right? You get this value of phi, because this is not going to be, if you multiply through by minus 1, so you're going to have phi squared plus phi minus 1 equals 0. So if you solve this, you end up getting this, basically. So I think that in the previous video I had done this, so that's why I'm not bothering so much about it. So now if you consider okay, let me write this. Stop heading for this. Runtime analysis of a divide and conquer algorithm. This is a popular thing in algorithm analysis, divide and conquer algorithm. Okay, so consider a divide and conquer algorithm with the recurrence relation. So the recurrence relation now is T of n equals 2T of n divided by 2 plus big O of n. Okay. So this recurrence represents an algorithm that divides the problem into two subproblems, each of size n over 2, and does linear work to combine the results. Okay, so this is the division into two problems, and this is the linear part. So um so this is the indicator for the two subproblems. Two subproblems. And this n is what indicates that what is the kind of work that is done is linear in nature. So it takes a bit less runtime compared to maybe things like quadratic. And does linear work to combine the results so that we can use a generating function. We can use a generating function to solve for T of n. Now, the recurrence can be modeled as a generating function and solving it results in a time complexity of T of n equals big O of n log n. So that's now linear log. So this is what is called linear, or is it linear log or log linear? I think it's linear log or log linear, most likely log linear. I'm not really sure which is which, but I mean, this is linear, this is log. That's basically the idea. Okay. Now with that done, so finally, thus generating functions allow us to derive the time complexity of recursive algorithms effectively. So, I mean, I have a plan to make a playlist on algorithm analysis. So let's hope I get around to doing that. So watch out for that. Of course, I still have other videos on applications of generating functions in areas like physics and biology, especially focusing on population growth model. And then I also have one on cryptography and data structures. So you don't want to miss out on any of this. So subscribe to this channel and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are. And also comment, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great teaching. Till I come your way again, keep doing maths right. Bye.